Today we're going to start the notes on chemical reactions. And just to dive right into it, chemical reaction is defined as a process in which one or more substances are changed or converted into one or more different substances. This is also referred to as a chemical change. And just loosely defined, reactants can be viewed as what you start with, and products defined as what you end up with. To use an analogy like cooking, reactants are like your ingredients, products are what you end up with. And you've also learned 4 signs or 4 indicators that a chemical reaction has occurred earlier this year. First one would be change in color. Another, change in energy, which would probably be considered like change in temperature. Could also mean production of light, because that's a change in energy, because light is energy. Third sign that a chemical reaction or change has occurred would be production of a gas. Lastly, formation of a new solid, or how we would call that as a precipitate. Right, that would typically be observed when, for example, you mix 2 clear liquids and it becomes cloudy or foggy. That cloudiness or fogginess is the solid being formed, where those particles meet each other in the liquid. So a chemical equation represents with symbols and chemical formulas what happens in a chemical reaction or change. And one thing that always has to be observed when balancing a chemical reaction is that the law of conservation of mass has to be obeyed, which means that the matter can't be created or destroyed. So what that boils down to is the mass of the reactants has to equal the mass of the products. So for example, if you start with 100 pounds of reactants, if all of those are converted in a chemical reaction, let's say just a generic chemical reaction of A being converted to B, you start with 100 pounds of this, you should end up with 100 pounds of this, if 100% of it gets converted from reactants to products. So because of that, the number of atoms you start with of each element present in the chemical reaction has to equal the number of atoms produced. And so that's how we can make sure that our chemical reactions are balanced. So I'm going to show 2 different ways to balance a chemical reaction. One using particle diagrams, the first method, and then show how to use basically balancing by just atoms. Right, so this first one is would be geared towards more visual. If you're more in visual learning and that works better for you, then this definitely can be the method that you use. If not, then you can try the other method that you most likely learned in science class in 8th grade. But anyway, this first one, we got N2, and we're going to use filled-in circle for to represent nitrogen and open circle to represent hydrogen. So N2 is a diatomic element, so the particle diagram would look like that. Hydrogen would look something like this, and the NH3, the nitrogen trihydride, or ammonia as it's commonly referred to, would look something like that. So if we want to pick one of these elements and see it and do our best to balance it, I start with just with the nitrogen. I notice I have 2 nitrogen atoms on this side of the reaction. I look over here, I only see 1. So I need more nitrogen on this side. I can't just add a nitrogen atom to balance it. Right? This nitrogen comes bundled in a package. So I've got to add 1 whole more NH3. And at this point, my nitrogen is balanced. I've got 2 over here, 2 over here, but I've got 6 hydrogen over here, 3 and 3, so 6 total hydrogen, and I only have 2 over here. So I need more hydrogen. So I need to add another 1 there, and lastly 1 over there. So now I've got 6 hydrogen here, 6 hydrogen there, and I just put these coefficients in the blanks to represent how many of the molecules or particles are needed. Now, as I mentioned in class, if you're viewing this again after going over this class, do you need to put the 1 here? No, not necessarily. It's not required. If you don't see a 1 in front of something in a chemical reaction, it is assumed to be a 1. Now, I would just strongly recommend, while you're doing this, is just get in the habit of putting 1 there. Just so that if you're going back and checking your work on a test or a quiz or even worksheet, that when you come to a blank, you don't have to think in your head, wait a minute, did I actually balance that and it's supposed to be a 1, or did I just forget to put something there? So I think it will be in your best interest, just put a 1 so that you know that you've gone through and balanced it. So when you go back and review your work, you know that you've at least done the balancing. Now the second example, we got mercury, which is going to be the closed circle this time, and we got our mercury 2 oxide, and this is decomposing into just elemental mercury and elemental oxygen. So if I start with either of these elements, like the mercury, I note the mercury in this case, I've got 1 here and I've got 1 on this side. So that's balanced, but I've got 1 oxygen here and I've got 2 over there. So the oxygen's not balanced. So I need 1 of these. So that has balanced my oxygen, but now my mercuries are not balanced. So I need to put another one here. Now I do a check, 2 and 2 for the mercury, 2 and 2 for the oxygen. So I am balanced. Now the third example here, I'm going to use a closed circle to represent the iron. Now here I got this big particle, Fe2O3, or iron 3 oxide for those of you playing along at home. Again, if I start with my iron, okay, now I had 2 over here, I only had 1, now I've got 2 and 2. So my ions are balanced. Go on to my oxygens, and I like, wait a minute, I've got 2 here, I've got 3 here. Well, it's not going to work. So I need more oxygen over here. So I add another oxygen molecule here, and now I've got 4, but I've got 3 oxygens over here. So my oxygens are still not balanced, and I need more oxygen over here. And I can't just add a single oxygen atom. I've got to add whatever particle the oxygen is present in. So I get the whole thing. Now I've got 6 oxygens over here, only 4 over here. I need to add 1 more O2, and now my oxygens are balanced. But then now I need to make sure everything else was balanced. And I've got 4 iron here. I've only got 2. So I need to add 2 more. Now final check, 4 iron, 6 oxygen, 6 oxygen. I am balanced. All right. Now, going on to the next page, just some blanket terminology. If a plus symbol is used when you have more than one reactant and or product to separate them as you're writing, so they don't get confused. into thinking it's all one big thing. The arrow that you've seen is what separates the reactants from the products. Basically means that, that's the separation of the reactants products, so like A going to B and whatnot. If the reaction is reversible, you will see the arrow written either as a double-sided arrow like this, or it could be two separate arrows, each pointing in the opposite. If you see a symbol like this between the reactants and the products, it tells you that is a reversible reaction. What that means is, depending on the conditions, the reaction might, the reactants might be converted to products, and or some of the products will be converted back into reactants. It's very common in biology or biochemistry. You see little subscripts that are letters after a formula. That is telling you the state of matter that is the material is in. S makes sense, stands for solid, L for liquid, G for gas. And another thing you might see as a subscript after the chemical formula is AQ, and what that is telling you is that it's aqueous, which means that the material is dissolved in water. Okay, so those are the letters you may see after a chemical formula, telling you the phase, the state of matter it's present in, solid, liquid, or gas, or whether it's dissolved in water or aqueous. If you see a triangle above the arrow, that means the reactants are being heated. The heat is being added to the system. And if you were to see some type of chemical formula or elemental symbol above the symbol, above the arrow, that means there's a catalyst present, and that is telling you what the catalyst is. In this example here, I just put the elemental symbol for platinum, and that would just if you saw whatever formula or symbol above an arrow, that's just telling you that one, that there's a catalyst present, and two, what the catalyst is. So in this case, if you saw PT above the arrow, just means that you've got platinum is being used as a catalyst. And what is a catalyst? Well, you may remember from bio last year, but the catalyst is just defined as a substance that speeds up a chemical reaction without being consumed. Means that it's present before the reaction starts, it's present after the reaction ends. It is not a reactant or a product, technically. It's just providing either a surface for the reaction to occur faster, or as we learn a little bit more next semester in the kinetics unit, it basically provides a lower activation energy pathway for the reaction to occur. So, skeleton equation. This is defined as just a chemical equation that doesn't have the coefficients present. It's basically what you have come into contact in the past. Just basically is an unbalanced reaction. Now, in the past, in your prior science classes, the skeleton equation has been given to you, and you've just been tasked with, okay, balance it with the coefficients in front. Now, one of the things that you'll be learning how to do this year is how to arrive at the skeletal equation based on either the words of, a word description of all of the reactants and products, or as you'll see on a couple pages from now on the notes, basically given two reactants, being able to predict what products. So before we get to balancing these reactions by counting up the number of atoms, we just want to make sure that we are pretty confident in our ability to look at a chemical formula and determine how many atoms are represented there, and then take into account the presence of coefficients out front, which is what these numbers over here, like 3, 4, and 3. So first of all, start off kind of simple. If you see the formula Br2, Well, that's telling you that I've got 2-bromine in that formula. If I look at the next example here, Cu2O, or copper 1 oxide. This formula tells me that I've got 2 copper and 1 oxygen present. Next one's a little bit more difficult, possibly. We've got calcium phosphate. Got 3 elements. And we've got some subscripts and parentheses and whatnot. But if you've got 1 particle of these, of calcium phosphate, that means you've got 3 calciums. You've got 2 phosphorus and 8 oxygens. Now coming over here to magnesium phosphide. This means we have 3 magnesium phosphides. So the number of magnesiums that would represent is 3 times 3, 9. And 3 times 2 for the phosphorus are 6. Notice this gets distributed and / multiplied by each of the subscripts in the formula. So it's not additive. So it's not like 3 plus 3 is 6 and 3 plus 2 is 5. Next one. Got sodium perchlorate. Good habit to get into as practice is just kind of be naming these compounds in your head as you go through, making sure that you are correctly naming them. I've got 4 of these sodium perchlorate particles. That represents 4 sodium, 4 chlorines, and 4 times 4 are 16 oxygens. In our last example, aluminum sulfite has 3 elements present. If I've got 3 aluminum sulfite, that represents 3 times 2, or 6 aluminum. And here's where it gets a little bit trickier, is that, right, you've got 3 aluminum sulfites, and in each particle, you've got 3 sulfites in them. So basically, in 3 of these particles, you have 3 times, now 3, 9 sulfite ions. So 9 sulfite ions represents 9 sulfur and 27 oxygens. Okay, so these are the ones that possibly give folks a little more trouble as far as trying to figure out, how many atoms are represented by everything in the formula with coefficients involved. Okay. So the method that you'll be looking at next for balancing reactions is most likely how you learned or were taught how to do this in middle school science, with this additional step, which we'll cover later this unit. And first, you need a correct skeletal equation. Second, you just want to start with any element and then start to balance it. Put a coefficient in front and see, balance that one and then move on to the next element and so on and so forth. One thing to keep in mind to make your life a little bit easier is if you notice a polyatomic ion that is present on both sides of the reaction and it isn't changed at all. For example, if it's sulfate on one side of the chemical reaction and it's still present as sulfate on the product side, if it's present in both sides as sulfate, then just balance it as a single unit. Basically treat it as an atom as opposed to balancing the sulfurs and then balancing the oxygens separately. So you balance the elements one at a time using coefficients. And keep in mind, this is a trial and error type of method. It's an iterative method. So if your beginning coefficients don't work, then just try something new. And you'll see on this on the next page. So sometimes it's best to, especially, you're going to see me balancing these things with pen, red pen specific, but it's probably not the best idea that you want to be doing. Using a pencil is probably best so that you can erase and not get as confused. The coefficients, right, those are the numbers that go in front of the formulas. Just a reminder, you cannot change the subscripts in your skeletal equation to balance, to make your atoms balance. Like you can't change the formula of NaCl into NaCl2 because you need to balance the number of chlorines on one side. So that is a no-no. You can only balance things by changing the coefficients in front. And the last step is you need to make sure that your coefficients are as small as possible. Like if your coefficients, like if we just look at the if we revisit this reaction from the other side, let's say that you were having a bad day and you got this to balance as 2, 6, and 4, which does balance, right? 2, 6, and 4. However, you need to reduce the coefficients as much as possible, kind of like reducing a fraction. So you notice if you notice that, wait a minute, these coefficients are all divisible by 2, or 3, or 4, or whatever, you need to do so. Okay, so just keep in mind you do need to reduce whenever possible. So let's do a little bit of practice. So on this first one, again, it's trial and error, it's iterative, so if you don't succeed at first, try again. So let's say I'm just going to pick carbon, I'm going to put a 1 here. So I look on this side, where's my carbon containing compound, or whatever, how the carbon is present over here. If I've got a 1 here, that means I have 1 carbon on this side. I need to have 1 carbon over here, so okay, a 1 balances the carbons. Now I need to check the other. So this 1 CO means I've got 1 oxygen here. Okay, so I need to make sure I've got only 1 oxygen over here, and oh, wait a minute, the oxygens have to come in pairs. So I know that 1 is not going to work. So I'm going to bump that up to a 2. So 2 carbons over here makes this a 2. My carbons are balanced. Now I've got 2 oxygens now on this side. I can now balance this because 2 oxygens means I've got 1 of these. Okay, now let's say you were having a bad day and you, for some reason, were not able to get this to balance with 2 in front of the carbon and the carbon monoxide. Again, just saying, had a bad day. Now the next step would have okay, I'm going to bump this up to a 3. So okay, if I've got 3 carbon here, 3 carbons over there, 3 oxygens over here, wait a minute, oh, that's not going to work. I'm going to bump that up to a 4. So 4 carbons, that means 4 over here. 4 oxygens, that means I can get to balance with a 2. So I'd end up with 4, 2, 4. And hopefully you'd recognize, wait a minute, these are all divisible by 2. So I have to do so. So I have to bump that, 2, 1, and 2. So you'd end up with this. So that's what I'm saying is it's iterative, it's trial and error. Even if you weren't able to somehow, probably doesn't, you probably can't understand in what world you wouldn't be able to balance this with at the 2s or even 4s. But if you couldn't even get to balance with 4, if you went up to 5, it wouldn't work. But 6, you'd end up 6, 3, and 6. You notice, wait a minute, they're all divisible by 3. You'd get so on and so forth. For those of you who might be a little stronger in math, one thing that you might notice, right, if math is more your thing and numbers, algebra and arithmetic come a little bit easier to you, one thing that you can also do is, for example, if I put a 1 here and a 1 here, you notice I can't get this to balance with a whole number. This coefficient would have to be basically a 1/2. If you are comfortable with math to this level, then you would notice, well, how do I make 1/2 into a whole number? Well, I just have to multiply it by 2. And so if I multiply everything here by 2, I end up with 2, 1, and 2. So that's another trick that you can use to balance equations. Like if you start with a number here and you end up with something's going to be a fraction to make it work, well, how do you get rid of that fraction? Just take care of that mathematically, and that should give you the correct coefficients as long as you multiply everything by that to get rid of the fraction. Okay. Again, I'm just trying to give you as many tips and tricks to make your balancing less difficult. Now, if we move on to the next one, I've got things present. I've got silver, I've got N, I've got O, I've got copper on both sides. And then you may notice, wait a minute, I've got nitrate over here. I've got nitrate over here. It didn't change. It didn't, none of it came apart. I don't have like any nitrogen and oxygen or anything else. So I'm going to treat this nitrate ion as a unit. Just like any other, I would treat the silver or the copper and just balance it just as NO3 and not have to balance it as nitrogens and then try to balance it as oxygens, because that might be a little more difficult. But again, I'm going to start with just put a 1 somewhere and see if it works. So if I put a 1 here, that means I've got 1 silver. Here's my silver over here, so I'm going to put 1 there. So now my silver's balanced. Now that also tells me I've got 1 nitrate over here. And wait a minute, I need a 2. So that means a 1's not going to work. I'm going to bump this up to a 2. That makes the silver a 2. Now I've got 2 nitrates. 2 nitrates are in this. I can put a 1 there. And lastly, 1 copper, put a 1 there. So I'd end up with 2, 1, 1, and 2. Now, over here, remember this method that I had mentioned? If you were going through and you got a 1 and a 1, you'd also be able to get this to balance with a, with a 1 here and a 1 here. To make this work, it'd be a 1/2 and a 1/2. And then you could just double everything and arrive at the same thing. Again, that is if you're a little bit, more advanced and or more comfortable with math. Start the next one. Again, if I start with a 1 there, I look over here, oh, wait a minute, aluminums have to come in pairs. So 1 doesn't work, I'm going to bump that up to a 2. And a 2 here means I can have a 1 there. So my aluminums are balanced, but now I've got 3 oxygens over here, and oxygens over here have to come in pairs. So I know that's not going to work. I bumped it to a 3. Wait a minute, 3 aluminum, I need 2 aluminums over here, so that's not going to work. So I bump this up to a 4. 4 aluminums mean that I can have 2 over here. So 2Al2O3, that's 4 aluminums. My aluminums are balanced. Now I've got 2 times 3 is 6 oxygens. It's an even number, so I'm going to get to balance. So 4, 3, and 2. Now, both of these are a little bit more difficult, but these kind of illustrate one tip that will be good to understand, is that when you are looking at a reaction, you kind of want to have in your mind what element you want to start with, or more importantly, what element you don't want to start with as far as balancing. And if you look at this first reaction here, you notice I've got hydrogen in this compound, I've got hydrogen in this, and I've got hydrogen in this. If you've got something that is present in almost everything, you want to save that for the last. You don't want to start balancing with hydrogen here. Okay? You'd want to start with either sodium or oxygen. And then when you're looking at this one, you notice, wait a minute, I've got oxygen here, I've got oxygen here, and I've got oxygen here. You do not want to start with the oxygen. You want to save the oxygen to balance for last. I'm not saying you can't do it that way. It's just be the equivalent of, in having 2 or 3 unknowns in one reaction and or one equation in math and trying to solve for it. It's going to be a lot more guesswork than like a more, I would say, educated trial and error. So in this case, I'm just going to start with sodium. I'm just going to put 1 there. You know, way that I approach this, I always start with a, my technique is I just start with a 1 and see where it gets me. And then if I need to change it, I change it. You notice, yeah, you do need to change it quite a bit, which is great when you're working in red pen. But if I got 1 there, put a 1 there. Sodiums are balanced now, 1 and 1. Now remember, I do not want to do the hydrogen next. I want to do that afterwards. So the next one I want to work with is oxygen. I've got 1 oxygen written over here. So I need a 1 here. And that tells me I've got 2 hydrogens on this side and can only have 2 hydrogens on this side. Well, I've got 2 hydrogens here. This single sodium hydroxide is taking up 1 of them. That leaves me with 1 hydrogen left. And hydrogen has to be a 2 over here. So again, if you're a little bit more comfortable with math, you may notice, well, I could balance that with a 1. 1/2, I'm sorry. And then you could just double everything to get rid of that. But if you didn't recognize it, you just start over, bump this up to a 2. Now that makes a 2. Makes this a 2. So the sodiums are balanced. 2 oxygens now. I need 2 waters. And now I've got 4 hydrogens on this side. The 2 sodium hydroxides take care of 2 hydrogens, leaving me with 2, and that's going to be a 1. And I'm balanced. And this one you can try on your own, but this one's a little bit more complicated, but you will get it to balance with these coefficients. Now, this is the beginning of the new content. And it's not necessarily new. It's just now you're using your naming skills from the prior unit, and we're going to apply those because here we want to write a balanced chemical equation from the words. And so that means we need, or you need to come up with the correct skeletal equation on your own before you can then start to balance it. So that's where naming is very, very important. So, couple things. If you see the name of an element and it's not a compound, just write it, the symbol for the element. Just have to remember the Brinkelhoff elements, the 7, that if they are not in a compound, if they're in their elemental form, that they're in the diatomic state. And we want to get some practice, including with the state symbols, solids, liquids, and gases. And just a brief review of the naming. Remember, ionic compounds, no prefixes. Where, typically ionic compounds will be solid unless they're dissolved in water. Covalent compounds could be anything, solid, liquid, or gas. You'd have to be kind of told that. And acids are typically dissolved in water or aqueous. You use your acid naming rules too. So, the word equation we want to balance here is typed out down here. Solid magnesium metal reacts with gaseous carbon dioxide to produce solid magnesium oxide and solid carbon. So in this first example of doing this, we just want to look at all of the things that are going to be in our equation, and we're picking those out of a sentence. We see solid magnesium metal. Okay, so we're just going to have magnesium metal. Okay, carbon dioxide over here to form a solid magnesium oxide and carbon. So these are the 4 formulas or symbols that we need to come up with on our own before we put them into our chemical reaction. And we also need to be able to determine, hey, what is our reactants, what are our products? But magnesium, right, is Mg. Magnesium oxide is MgO. Right, magnesium's +2. Oxygen is -2 for an ion. Carbon dioxide, that's right, covalent, so it's CO2. And carbon, the element, is just C. Right? Oftentimes people might get confused and think that carbon is one of the diatomic ones, because when you say the word Brinkelhoff, well, you kind of hear a C word, a C sound, but Yeah, just keep in mind that's chlorine and not carbon. So carbon is not C2, it's just C. So trying to parse this sentence to figure out what's a reactant, what's a product, it says solid magnesium metal reacts with gaseous carbon dioxide. Okay, so this is basically saying these are our reactants. You see the to produce, that is telling you, okay, that's the arrow. So this reacts with this, so it's basically this plus this to produce solid magnesium oxide and solid carbon. So our skeletal reaction is going to be magnesium metal and solid reacts with carbon dioxide gas to produce solid magnesium oxide plus solid carbon. So there is our skeletal reaction. Now, just like we were doing before, we just need to pick an element and start balancing it. So again, if I start with a 1 here, to balance my magnesium, okay, there's my magnesium. Now I've got 1 oxygen over here. I look at my oxygen-containing compound over here, I need 2. All right, well, need to bump that up to a 2. So 2 magnesium, 2 magnesium. It's balanced now 2 oxygens. 2 oxygens, I can put a 1 here. And the only thing that's not balanced is the carbon. Got 1 over here. All right, that works. Now, one thing I want to point out is, does it matter which one of these is listed first? No. Right, the order that these are in, like, for example, you could write CO2 plus, plus 2 magnesium in the arrow, and then carbon plus 2 MgO. The order doesn't matter what they're written, as long as they're on the correct side of the chemical reaction. Okay, so the reactants just have to be in the reactants, products have to be in the products. The order doesn't matter whatsoever. Next one. So here in words, you got solid iron 3 oxide reacts with carbon monoxide to produce solid iron and gaseous carbon dioxide. So if I'm reading this, okay, I got 1 material, 2 materials, 3 materials, and 4. And right, just on these 2 examples, we kind of just put some areas up here just so that you can make sure that you have the correct formulas for everything before you put in the skeletal equation. And you notice this reacts with this. Okay, so here are my reactants. The to produce, okay, well, there is basically my arrow. Solid iron and gaseous carbon dioxide, those are my products. So now I just need to, these are the 4 chemical formulas need to be able to provide. Carbon monoxide, CO, carbon dioxide, CO2. Iron, so Fe. And iron 3 oxide, well, it's iron with oxygen. If this is plus 3, oxygen is minus 2. So to get this to work, I am going to need 2 iron and 3 oxygen. So I can put this down here. Solid iron oxide reacts with carbon monoxide, and it doesn't say the state on carbon dioxide or carbon monoxide. If you ever encounter this on a test or quiz or whatnot, where it gives you and you're asked to provide the states of matter. If it's not given to you, just ask me if it was omitted on purpose or whatnot. This one I probably just need to update, say gaseous, but hopefully you would be able to know that at room temperature, which unless specified elsewhere, we're just kind of assuming these things are at room temperature, is that at room temperature, both carbon monoxide, carbon dioxide would be gases. Solid iron over here, and gaseous carbon dioxide. So we just need to balance this. I'm going to cross this one out just now, just because I've got it down here. I don't want to confuse anyone. That was just earlier in this problem, just trying to identify what is what in that product. So again, you just want to start with something, put a 1 in front of it. If I put a 1 there, that means I've got 2 iron. And remember, if I'm looking over this reaction, you notice I've got oxygen in this compound, and this compound. So I do not want to start with the oxygen. I want to end with the oxygen. My game plan for this is to balance the iron first, then the carbon, and then see if the oxygens can balance. So I've put a 1 here. That means I've got a 2 there. Then if I'm looking at the carbon here, okay, I got a 1 there. I put a 1 there. So everything is balanced here except for my oxygens, and I need to see what's going on. And wait a minute, I've got 3 plus 1, 4 oxygens on this side. I only have 2 over here. Well, that's not going to work. I'm going to bump my carbon up here, and I'm going to shift my approach a little bit in the sense that instead of starting with the iron, I'm going to start with the carbon, and then the iron, and then the oxygen. I've got 2 carbons here, I put 2 here. That means my carbons are balanced, but I've got 4 oxygens over here, and I've got 2, and if I even have just a 1 here, well, that's going to be 3. That's not going to work. So I'm going to bump this up to a 3. 3 carbons, 3 carbons. Carbons are balanced. I've got 6 oxygens here. I've got 3 oxygens taken care of here. So I've got 3 carbons left over, so I can put a 1 here. And that means I can balance this with a 2. So my coefficient would be 1, 3, 2, and 3. Now you noticed, even though I said at the beginning that typically you would want to save the oxygen for last, in this particular reaction with these compounds, you notice I balanced the carbons first, then I balanced the oxygens because 2 of the 3 oxygens were kind of determined, and I balanced the oxygens so that I could get a whole number coefficient here, and then because the iron was by itself over here, that would make it very easy to balance. So again, I'm trying to give you the best tips that I can provide to you, but you know, it a lot of times comes down to a trial and error, and just the more practice, the more different approaches to balancing that you will get better at. Right. That would be it for this video, and we'll see you in the next one.